Hi everybody, welcome to the next lecture on Multimediale Werkzeuge, this time more about color. So first about color mixing. So basically there are two types of color mixing, and the first type is the addition of light, additive mixing. For instance, this is the case for displays. Displays have lights being emitted from the different pixels as primary colors, and when those little primary colors are turned more or less on, and then what happens in the distance is we have a additive color mix. And additive color mix has the property that a color plus a complementary color results in white. So here's an example. So again, here the sensitivity curves of the cones. And here's this example. So horizontally we have the wavelength, vertically the intensity, and then we have a light which is having this distribution that we can see here in this curve. So it has a maximum intensity close to 700 nanometers, for instance. Then there's another light source, and this has its color, its maximum intensity at somewhat smaller wavelength here. And if you shine those two lights together, then basically you have those two peaks appearing together. Right? You have color A plus color B. So in the physical domain, you can clearly see that there is a mix of two colors. But the eye, when it observes this light, just sees a mix, a color mix. So instead of seeing two different colors, it sees one new color, which is the color mix. Right? So this is again a property of the brain, that it makes those color mixes so that we see different colors. So when you would analyze this mix, for instance, with a prism, you would still see that it consists of colors of different wavelengths. The other type is the so-called subtractive mixing. This is obtained, for instance, using color filters or reflections on colorful surfaces. So when you have a reflection or a filter, usually they subtract a given wavelength, like here. Right? You have, for instance, white light, and then around 700 nanometer you have an absorption. Right? It's either coming from a filter or from a reflection from a colorful surface. So in this reflection, this is, for instance, absorbed from molecules who have resonance around this wavelength. And if you have a different color on a nearby surface, then you have, for instance, this dip, and it's a little bit at a somewhat smaller wavelength. And if you apply both of those, then you get two dips, right? So now you have a color mix, but now it's a subtractive mix because you subtracted wavelength from an originally white light. So after mixing, say after you apply two color filters, one after the other, or you have paints one on top of each other, then this is what you get, right? This subtractive mix. And subtractive color mixing has the property that a color plus the complementary color is black. So basically you subtract everything and then nothing is left. And primary colors for the subtractive mixture are the complementary colors of additive mixing. So you have different primary colors for subtractive mixing, and they result from being the complementary colors of additive mixing. And that makes sense because remember, when we mix a color and a complementary color, we get white. So since we subtract something and subtractive mixing, this corresponds then to the complementary colors. Yeah, so here are the primary colors for additive color mixing. Here we have green, red and blue. And here you can see in the middle it's white. And then across you have the complementary colors. So you can see across from blue we have yellow. So yellow is the complementary color of blue. And this is one of the primary colors of subtractive color mixing. Then the complementary color of red is this green-blue, this cyan. And then complementary of green is this magenta. Yeah, so these are the primary colors then for subtractive color mixing. Here you have the yellow, cyan and magenta. Right, and that's why you have different sets of primary colors depending on if you do additive mixing or subtractive mixing. Yeah, and this can also be seen from our color triangle from last time. Yeah, so how do we separate color information from brightness information? This would be interesting because color information needs less spatial resolution for the eye, as we saw from the contrast sensitivity function. So it can be useful for compression and transmission. So given the red, green and blue components coming from a camera, right, these are the usual outputs from a camera, we would like to create a luminance signal. Signal Y, which is kind of an artificial rod signal, right? Remember, the eye has many rods, but they are only sensitive to the luminance, the intensity of the light, but not the color. And that's the role that the Y component now plays. So the Y component is the weighted average of the three primary colors coming from the camera, and those different factors come from the according sensitivity of the eye to those different primary colors. So here, sensitivity of the eye for the wavelength regions of each primary color. And also Y is non-negative. And that makes sense because RGB are non-negative. These factors are non-negative, so Y must also be non-negative. So the resulting color transform is called YUV, and this is basically the result. So we have the Y, and then we have two more components, U and V, and they simply result from B minus Y and R minus Y. And it is designed to be so simple because originally it was supposed to be done by analog electronics in old TV sets, and this was simpler to implement. That's why they chose such simple formulas. So if you put all together here in a matrix, this is what we get. So here the first row is the coefficients for Y, and the next row we have the resulting coefficients for U, and then the ones for V. And you can see here for U and V we have negative coefficients. So U and V now are no longer non-negative. They can also have negative values. And an important property of this transform is that if we have monochrome images, black and white, then the resulting color components U and V will be zero, right? Independent of how much light we have, how much brightness, they will be zero. So here's an example. RGB have the same value, say 1. Then Y will be 1, and then U and V will be 0 because these coefficients, they add up to 0. Yeah, so a monochrome image, black and white, has a flat light spectrum, and hence all primary color filters of a camera have the same output. So for monochrome images, we have U equals V equals 0, which means no color signal needs to be transmitted, which was important for the analog NTSC and PAL TV standards. This is also important for digital standards because if you have many zero values, then they can be encoded with fewer bits. Okay, so now we have the color signal separated from the brightness or luminance signal, right? using color transforms. So the color information can be transmitted or stored with lower spatial resolution using the contrast sensitivity function. So we saw last time that the peak of the spatial resolution is clearly lower at lower frequencies than for luminance. So that's why we can save bits at that point. So this is also used in the analog TV. So the luminance Y uses approximately 5 megahertz bandwidth, but U and V just approximately 1.3 megahertz. So it's clearly lower, so that's maybe 1/3, right? So a lot of compression just going to the color components to use the fact that the eye has so many fewer cones for color than rods for luminance. Okay, so in digital, this means Y would have the full pixel raster, meaning full resolution, but then the components U and V would only have a downsampled pixel raster. So horizontally and vertically, they would have the half pixel grid, which means they have half the edge lengths for the components U and V. So that means you have just 1/4 of the pixels necessary for U and V. So that already gives you a lot of compression just going to those color components. There's also an alternative color transform which is used in the American NTSC color TV standard, which is the YIQ color transform. And it has a slightly different transform matrix, color transform matrix, which you can see here. So the Y is the same, but U and V is slightly different. It also has the same principle that if you have the same values for R, G, and B, then I and Q will be 0. So they are only active if we really have color in the image. So again, separating the color from the luminance again works. And if you compare the color spaces, basically I and Q have slightly rotated coordinate vectors compared to the U and V. So you could think of I and Q having a coordinate axis which is about 30 degrees rotated and slightly stretched or compressed. So here the color space of YIQ is stretched and rotated about 30 degrees compared to YUV. And why is it done? YIQ has the advantage that it needs even less bandwidth for the Q component. Right? I again has 1.3 megahertz, but Q needs just 0.5 megahertz, so almost 1/3 reduction. So that's pretty good. So this is actually also something that could be used for digital compression, but because YUV is so much more widespread in the world, also the digital versions have a YUV. Yeah, so then there's also a little insert here for embedded systems for the projects. So this is relevant for the Internet of Things, and this is the inter-IC communications, I2C. So I2C is a standard for communicating between integrated circuits on the board, or as in this case, between boards. So for instance, the Raspberry Pi and the Arduino computers have the I2C communications port for external hardware like servo motors and accelerometer. This port can be recognized with the pins labeled SCL for serial clock and SDA for serial data. You need to connect the correspondingly labeled pins of computer, the master, and external hardware, the slave, the ground pins, and the power supply, either 3.3 volts for the Raspberry Pi or 5 volts for the Arduino. And you can read more about the communications protocol, which is standardized in this webpage, i2c.info. and also in this Wikipedia link. And the I2C protocol gives each device a 7-bit address such that theoretically 128 devices could be connected to it in parallel. Right? So that's very convenient. We just put them all parallel and it still works. The 8th bit is to signal read or write access, because the data can go in both directions. To communicate with a device, the master signals the desired address, so which device, and read or write, so if it wants to send data or receive data, followed by information bits, and the information bits go into one or the other direction. The clock from the master synchronizes the communications with the slave. So the clock is there so that bits can be distinguished. So here's an example. This is the communications of the Raspberry Pi in Python with the accelerometer MMA8452Q. So this is, for instance, for the two-legged robot. The two-legged robot needs an accelerometer for balancing. So since it only has 2 legs, it needs to balance its body using this accelerometer. And for that we use I2C. So in Linux you can check the used I2C addresses with the command sudo I2C detect -y1. So here, very simple, it gives you the I2C devices connected. And then it returns the I2C address. So this can be used for checking to see if the expected address is there or if it's some different address. Yeah, so this is also good to avoid communication problems. So this can be used in the Python program below. So here we have import SMBus. So here SMBus is the library which allows us to communicate with I2C. And here we basically get an object, the bus object here from it. And here we define the I2C address of our accelerometer. So this is actually the default address for the board, but it actually can be changed. So the factory setting doesn't have to stay this way, and this needs to be done if we have 2 different devices which have the same address, then we need to change it. But if we just have one device, like one I2C device, then we can just keep this default address. Yeah, actually we will have more than one I2C device for the robot, because also the accelerometers are addressed using I2C, but they are using a different address. So it's fine to use the default. Yeah, so here is an example how to select a control register. So this has this address here, the hexadecimal 2A or decimal 42. And here we can put the sensor, the accelerometer, into active mode by sending this 01 word to this register. So we write this word to this register, and we do that by using bus. This is the object that we just created here. Write byte data. Here we use the address of our accelerometer. Then here we use the address, we send the address of the register to which we want to write. And here we send the data word to make it active, basically to turn it on. And then we can read data back from it. So here we send data, and now we can read back on the accelerometer data, the acceleration information. And we do that here by bus read I2C block data. So very similar, we have the address of the device, here the register that we want to read from, and here the number of bytes that we expect. So here this read function sets also the I2C connection into read mode, so that the device knows that it needs to send bits, and then it sends those 7 bytes that comes from this register here. So then the information goes back into this object data, and then we can, in this array data, let's say, and then we can basically combine 2 bytes each into a data word which represents the acceleration value. So that's done here in the next line. Here's the y acceleration. It takes the 2 data words 3 and 4. So each contains 1 byte, and we combine them into a 2-byte integer. So here data 3 times 256 plus data 4. So this is a 2-byte integer, and then we basically divide it here by 16 to get a certain value range. Right. So here you can also see how negative values are represented. So if the value is above 2047, then it's a negative value, and we subtract 4096 so that we get the correct negative value. And finally, we can divide by 1024 to get a float in the range of -1 to 1 for easier processing. So then the y acceleration is the integer y acceleration divided by 1024.0, which turns it into a float. Yeah, so this is how you would communicate with the I2C device, the accelerometer. Yeah, and for specific meanings of the registers and their contents, you need to study the data sheet of the accelerometer, which you can find here. So this is what you have to do for specific I2C devices. They have certain registers and certain code words, and they are described in the data sheet. So this one for this accelerometer is you can find here. Yeah, it's actually continuous here. So this is a PDF which contains the description. Yeah, and you can do the same in C, for instance, for the Arduino. For the Arduino, you can get this .h file, which you can include here. And this already contains information about this accelerometer, which makes the access a little bit more easy. So here you can see it creates this object, Excel, from this library. And then here you can see this Excel object has the function available, which tells the machine if it's connected or not, or on or not. And if it's available, then you can read values in using the function read, and then it copies the information to this object, and then you can access it with .cy and .cz, for instance. So fairly simple. Okay, so that's for this part of the lecture. Yeah, thank you for your attention, and see you in the next part.